Hi, welcome to the discussion of Cramer's rule in solving systems of linear equations. In this example, we'll be dealing with three unknowns. So consider a linear system 2x plus 12y plus 17z equals negative 32. This is the first equation. The second equation would be negative 3x minus 7y minus 8z equals 6. And the third equation is x plus 4y plus 6z is equal to negative 7. So to completely follow the Cramer's rule, we have to convert this system of linear equation into this form such that all x variable will be written as x sub 1, the y variable will be written as x sub 2, and the z variable will be written as x sub 3. In the past video, we already solved this using Gauss-Jordan elimination. And the result is that x sub 1 or the x value is equal to 9, x sub 2 or the y value is equal to negative 7, and x sub 3 or the z value is equal to positive 2. So let's get started. Basically, we have two steps to follow when we are using Cramer's rule. The first one is to compute for determinant A. So if determinant of A is equal to 0, Cramer's rule is not applicable. So we could use Gauss-Jordan elimination, Gaussian elimination, or simply elimination or substitution. Please don't be confused if you see this value because this is the same thing as determinant of A. So you can write it in this manner. It's like an absolute of capital A, but this is read as determinant of A. Now, if the determinant of A is not equal to 0, we can proceed to step 2, that is to solve for the x sub I is equal to the quotient of the determinant of A sub I and determinant of A. Let's see the perspective of these rules. So we have the linear system in x sub I forms. And the first step is to take the determinant. Again, you could write it in this manner or in this manner. So take the determinant of A. Capital A here is actually the matrix A, in which these are the coefficients of the x sub I. So for the first column, it should be the coefficient of x sub 1. The second column should be the coefficient of x sub 2. And the third column should be the coefficient of x sub 3. Please don't be confused if you see this symbol. This is not a matrix symbol. It's actually a symbol of an operation. And that operation is taking the determinant. It's very different from a matrix because you have to write it in a bracket form. Okay? So if the determinant of A is not equal to 0, then we can proceed to step 2, in which we take now the quotient of the determinant of A sub I and determinant of A. So this is the perspective. In solving x sub 1, this is now equal to the determinant of A sub 1 divided by the determinant of A. So to write the determinant of A sub 1, you just simply change the coefficient of x sub 1, which is 2, negative 3, 1. Change this to this value, negative 3, 6, and 7, wherein in our system, this is the value of the right side of the linear system. So for determinant of A sub 2, that means that you change the coefficient of x sub 2 into this value, and for the determinant of A sub 3, you also change the coefficient of x sub 3 into the values of the right side of the linear system. So that's the perspective. Let's start with solving this example. So using Cramer's rule, first step is to take the determinant of matrix A. First column, this is 2, negative 3, 1. Second column is 12, negative 7, 4. And the third column is 17, 8, and 6. Now notice that I have written and copied the first column, that's 2, negative 3, 1, and then the second column, 12, negative 7, and 4. I deliberately did this so I can show you a form of solving the determinant of A using the diagonal method. So in computing this is now equal to the first grouping minus the second grouping. Now, where does this first grouping comes from? The first grouping is actually coming from the product of the first diagonal. So I have 2 times negative 7 times 6. This is equivalent to negative 84. Negative 96 came from the product of 12 and negative 8 and 1. And negative 204 is the product of 17 and negative 3 and 4. So the first diagonal is going down. You just take the product and that would set you the first grouping. This is minus the second grouping. Negative 119 came from the product of 1 and negative 7 and 17. Negative 64 is the product of 4 and negative 8 and 2. And negative 216 is the product of 6 and negative 3 and 12. So there you have it. My first grouping is complete. My second grouping is complete. I now simplify the first grouping. This is negative 384. And then the operation is a minus. And then the second grouping is negative 399. Simplifying this, a negative and negative, that would be positive. The result now is 399 minus 384. And I have a value of 15. Now, since this is not equal to 0, we can now proceed to step 2. So step 2 is now taking the value of x sub I. So we start with x sub 1. This is equal to the determinant of a sub 1 divided by the determinant of a. Determinant of a is already 15. And all we need to do is write the determinant of a sub 1. Again, the determinant of a sub 1 is the matrix A, but the coefficient of x sub 1 is now replaced with the values of the right side of the equation. Now, I'll be using this method. However, I won't need to rewrite the first column and the second column because I'll be showing you another method. So I have the first grouping minus the second grouping. And this 1,344 came from the product of negative 32 and negative 7 and 6. 672 is the product of 12, negative 8, and 7. And then 408 is the product of 17 and 4 and 6. So we are simply multiplying the elements, which is the same thing as the method I use for this part. All right, so we go to the second grouping. The operation is a minus. So I have 833. This came from the product of negative 7 and 17. 1024 came from the product of 4 and negative 8 and negative 32. And then finally we have 432. This came from the product of 6 and 12 and 6. So it's like a heart-shaped method. And this is the diagonal method. Okay, so my first grouping minus my second grouping is now complete. The sum of my first grouping is 2,424. Then my operation is a minus. The sum of my second grouping is 200 or 2,289. Our divisor or the denominator is 15. So when I simplify this, I end up with 135 and you divide it by 15. I have a value of 9. So this is actually correct because we already solved this using the Gauss-Jordan elimination. We work out with x sub 2, the second variable. So x sub 2 is now equal to the determinant of a sub 2 divided by the determinant of a. And again, we now replace the coefficient of x sub 2 into the values of the right side of the equation. So this is negative 32 supposedly. That's 6 and that's negative 7. We can now apply the solution for taking the determinant. So I have 2 times 6 times 6, that is 72. Negative 32 times negative 8 times 1, that is positive 256. 17 times negative 3 times negative 7, that's positive 357. 1 times 6 times 17, that is 102. Negative 7 times negative 8 times 2 is 112. And 6 times 3 times 32. The result should be positive because 3 is negative and 32 is negative. So my first grouping came from the diagonal going down, and my second grouping is from diagonal going up. The operation again is a minus, so if I simplify my first group, I end up with 685, and my second grouping is 790. The difference of these two is 105, and divide this by the determinant of A is equal to negative 7. And then we move on to the last variable. So x sub t is now equal to the determinant of a sub 3 divided by the determinant of a. So we now change this column from the coefficient of x sub 3 to the coefficient or to the values of the right side of the equation. And now we proceed with our solution. the first diagonal, 2 times -7 and -7. That would give you a positive 98. 12 times 6 times 1 is 72. This one is -32 times -3 times 4 is a positive 384. Minus the second grouping. This is a diagonal going up. So 1 times -7 times -32, it should be positive 224. 4 times 6 times 2 is 48. -7 times -3 times 12 is positive 252. Again, the operation is minus. So the sum of the first grouping is 554, and the sum of the second grouping is 524. The operation is a minus, and the difference now is 30, and that is divided by 15. I have 2. There you go. So again, we have the values 9, -7, and 2. Using the Cramer's rule, we end up with a similar solution. So in summary, the first step is to take the determinant of matrix A, wherein this is an n by n matrix coming from the values or the coefficient of the variables. Second step is to solve for the variables already. So for general solution, that would be x sub I is equal to the determinant of A sub I divided by the determinant of A. If there are any questions, feel free to comment down below. This is the end of my discussion. Till next time, thank you for watching.